Okay, this is the LC circuit part two, and I was just showing you how these equations, how for every equation in mechanics, with the this is the mechanical oscillator, how there's the electrical oscillator, the LC circuit, has a counterpart equation, and I'll use this little space to tell you that the unit or the analogs so far that we've talked about is M, is L. K, the spring constant, is 1 over C. Let's see, X, how far you are from the equilibrium position. X is analogous to Q. And turns out that V is analogous to I. Okay, so let's go back. And so we have those right there. And now I'm going to say that A, if I take the acceleration, the derivative of V with respect to time, by the way, this is V max right here, because sine of theta oscillates between 1 and -1, so the maximum V can ever get is A omega. Same thing with I. The biggest I will ever get, the current I mean, is Q naught omega. Okay, now A is the derivative of this, so that's going to be negative A omega squared cosine omega t. What's the maximum A we'll get? It's A omega squared. Okay, now what I'm going to do is I'm going to take this equation, and you see that if I want to find out what F net is doing, I'll just multiply that times MA. So F net is MA, so that's M times A, and this is A. This is all assuming that you're starting you start your watch at X equals A. At time t equals 0, X equals A. And that's a negative sign. Okay, now the counterpart to this is that the EMF in the inductor is going to be L di dt. It's M times, you see how that's dv dt? M dv dt. And so just take this times, I'm going to take the derivative of this and multiply it by L. So the EMF of the inductor is negative L. And now I'm going to take the derivative of this with respect to time. So it's going to be a negative, make that a positive. It's going to be Q naught omega squared sine omega t. Okay, notice there's a one-to-one, see ML, A, how far back you pull it, how much you charge it, and omega. Okay, one other thing with omega, if you were wondering. Omega, when you're going in a circle, omega is how many radians you make in a second. Delta theta over delta t. But in simple harmonic motion, it's how many cycles you make. So it's cycles, 2 pi is one cycle. In the time, and the time that you take to make one cycle is the period. So that's 2 pi time over the period. And then so that's what omega is. So if I wanted to figure out how omega worked into all this, what the equation for omega was, it would be equal to 2 pi divided by, now I'm going to put the period of, say for this guy, what's this omega? Let's see, the period of this is 2 pi times the square root of M times the square root of LC. So omega, it looks like it's equal to 1 over the square root of LC. I'm not writing too well today, but that's a square root of LC there. Okay, let's look at it from an energy point of view. Okay, just like when we first did this with mass on a spring, we said that the energy at the beginning would equal the energy at any other point along the way. So we said the energy at the beginning is 1/2 kA squared. but it would equal the energy at any other point. So at any other given point in here, it's like not necessarily right at the center, but any other point a distance x away, it's got both elastic energy and kinetic energy. So it's going to have 1/2 kx squared, where x isn't as big as a, plus 1/2 mv squared. Well, the counterpart to that, I'm going to write it right underneath, is that at the beginning it's got 1/2. Now the capacitor has, the K is going to go to 1/C, and the A is going to be Q naught squared. So that's the initial energy in the capacitor. See how that's 1/2 Ka squared? That will equal some other time. At some other time it will equal 1/2 times 1/C times just regular Q squared, the Q at any given any other time as this swooshes back and forth, plus 1/2 mv squared, so 1/2 m, but m is L, and then V is I. This is the energy stored in the inductor. So it oscillates back and forth between those two. Let me just show you a picture of what I'm talking about here. So this is the LC circuit at different points along the way. Right now, all the energy is stored, we say it's stored in the electric field in the capacitor. So the capacitor is charged, and we say that the energy is stored in the electric field. So the total energy, ET, is basically equal to the energy that's stored in the capacitor. No, I messed up here. Forgot. I want to. This shouldn't be here. I'm going to put my thumb there. That red one shouldn't be here. Let me get rid of it. I meant to get rid of that. There, perfect. Okay, so when you close the switch, then what's going to happen is some of that energy is going to turn into, you're going to get a current. That current is going to flow through the inductor, and you're going to get a magnetic field in here. So we say that the energy now is stored in the inductor. And so, in fact, when this is completely uncharged, you might think the story is done. It's all uncharged. But here's the thing. There is a magnetic field now in the inductor. And when that goes to disappear, this is going to behave like a battery to try and push more current through. And that's why it's going to get charged up. It's going to charge up to positive sides. This will be positive now, and that will be negative. Kind of like the mass overshooting and going into the negative x territory. Okay, so at this point, all the energy is in the inductor then. Now your total energy never changes in here, but it just oscillates between energy stored in the capacitor and energy stored in the inductor. A brief moment later, all the energy that was in the inductor is now going to be back in the capacitor. So there you are. And then a little later on, it's going to go to discharge, and it will set up a field in here. And that field will have some energy. So it's just oscillating. See how the total energy is staying the same? But sometimes it's stored in the energy of the capacitor, and sometimes it's stored in the energy of the inductor. And the equation that you use to show that is this equation. So 1/2 1/C Q naught squared is equal to, I won't read that to you, but it's the energy at the beginning. This is the total energy. This is E equals E prime. So this is the E at the beginning. This is the E at some intermediate time. If I wanted to get I max, like the most current possible, well, the most current possible is when this doesn't have to split any with this. It's when the capacitor is completely uncharged. That's when you get the most current possible. In other words, if Q is 0, then that disappears. And so our maximum current then is just, let me solve for it. I can get rid of a half. And if I bring the L on the other side, that is I max. All right, thanks. Bye.